Today we're going to learn how to calculate the support reactions for a simply supported beam. Considering the simply supported beam in front of us, at both ends of the beam we have simple supports which enable the beam to freely rotate. At 6 metres from pivot point A, a point load of 60 kilonewtons is applied. In order to determine the reaction loads at pivot point A and pivot point B, first we draw in the reaction at A and the reaction at B. Now, the reactions at A and reactions at B can only occur in the vertical direction, and that is because the beam is free to translate in the x direction. Because of this, there cannot be a reaction force that builds up in the x direction, so the reactions only occur in the vertical direction. In order to calculate the magnitude of the reaction force A and the reaction force B, we need to sum the moments about pivot points A and pivot points B. By convention, moments taken in the anti-clockwise direction are positive. So now let's consider the moments about pivot point A. First we'll look at the 60 kilonewton load. And that 60 kilonewton load occurs in the clockwise direction. So by convention, that will actually be a negative moment. So we can say that the sum of moments about A is equal to negative 60 kilonewtons by 6 metres. And then the other force which is causing a moment about pivot point A is RB. So RB is actually causing the moment to occur about pivot point A in the anti-clockwise direction. And so again, by convention, that will be positive. So we can say plus RB multiplied by the perpendicular distance from pivot point A to the force where it's applied, and that is 6 plus 4 metres, which is 10 metres. All of this is equal to 0. And that's because the moment about pivot point A has to be 0 because there's no ability on a simple support to be able to restrain the beam against moment. As we said at the start, the beam's free to rotate at pivot point A and pivot point B. So rearranging this above, we get RB is equal to 60 times 6 on 10, which is equal to 6 by 6, which is 36 kilonewtons. So we have our magnitude for the reaction force B. To determine the reaction force A, we do exactly the same thing. We can say that the sum of the moments about B is equal to, and again let's consider the sign convention. So this time round, the 60 kilonewtons applied about pivot point B is going to cause a anti-clockwise direction moment about pivot point B, so that will actually be positive. Last time it was negative, but now it is positive. So we've got plus 60 kilonewtons multiplied by the perpendicular distance from pivot point B to the action of the force, and that is 4 metres. Then we have the reaction at A about pivot point B. This time round, the moment caused by RA about pivot point B is occurring in the clockwise direction. So that means that it's a negative moment. So we say minus RA times by the perpendicular distance from pivot point B to the line of action of the force is equal to 6 plus 4 metres, which is 10 metres. And again, as with the moment about A, the moment about B also has to be equal to 0. there's no ability to sustain a moment because the beam's free to rotate. So then we can rearrange for RA, and that is equal to 60 by 4 on 10, which is equal to 6 by 4, which is 24 kilonewtons. Now, one thing that we can do with all of this is to do a check by summing the forces in the vertical direction. And these forces would all be equal to 0 because it's a statics analysis problem. So if we sum the forces in the y direction, they are equal to RA plus RB minus 60 kilonewtons, and that's because the 60 kilonewtons is occurring in the opposite direction to RA and RB, all equal to 0. So we can check this. We can plug in our values for RA and RB. So RA is equal to 24 kilonewtons, plus RB is equal to 36 kilonewtons. And yes, it does indeed add up to 60 kilonewtons. Thank you for your time.